Come on, go away. Yeah. We'll have to live with the little bar. Oh, now there's nothing on the screen. How does that? Okay, you see something on Zoom? Okay, we're going. Okay, so summary. Riemann sums. We figured out how to handle the case of functions that are no longer monotonic. When you break up your interval into xi plus 1 equals xi plus delta x. To get a lower bound, you take the minimum value of the function. To get an upper bound, you take the maximum value of the function and use those times the width of the rectangle with Archimedes' principle to form lower and upper bounds on the true area under the curve. And then if those limits both exist, they're finite and they're equal, the Riemann integral exists. Fabulous. Come on. Go away. Yeah. We'll have to live with it. For the Riemann integral, we have a lazy S integral from A to B. It's a very compact, expressive notation. We want to recognize when we see that it's simply a fancy way to do sums. That thing on the left means to do these two sums and then take the limit as the number of rectangles goes to infinity, and hence the width of the rectangle goes to 0. And as long as the function is continuous, it's guaranteed that this Riemann integral exists, A and B both finite. Great. One of the things we noticed is that rectangles aren't the most efficient way to try to estimate the area. So we started using the trapezoidal rule, or simply trap-z for short. And as long as we know how to calculate the area of a rectangle and then the area of a triangle, you sum those together, that forms a trapezoid. And it's a very elegant formula. You take the function evaluated at the two endpoints of your interval, take their mean, multiply by the width of the rectangle. And then if the function is continuous, you can take the limit as that sum goes to infinity. So it'll then you'll be able to calculate values with with a smaller value of n, because in practice we don't go to infinity. Another kind of integral is the indefinite integral. So when a and b are fixed numbers, like from 2 to pi, it's called a definite integral because you've got definite area. When you let one of the bounds be a variable, you get what's called an indefinite integral. So this is really more vocabulary than a concept, because as soon as x is fixed, then it's the same integral that we were calculating before. But you realize then that integration applied to a function can give you another function. And that's important because, as we'll just a second here, that's how you undo velocity to get position. Right now, we have one family of integrals. Our integral table consists only of monomials, so functions to power k. Since I have x here, I put a different dummy variable. And the integral is x to the k plus 1 to the k plus over k plus 1. And that comes from knowing how the sums of integers from 1 to n with the integers raised to power k has a very specific form that leads us to this answer. And then we've only done one application of integration, and we just said it's true. You'll be exploring it deeply in Project 1. where if you have a velocity curve, you're going positive, then you back up, then you go positive again, etc. It looks like I stopped doing my filling in of the area. Your position at time t, it matters whether you started at the robotics building or your apartment or your dorm, because this just computes the change in position, not the absolute position. You need to add to it your starting position at time t0. When we get to differential equations, that will be called an initial condition. That's where you start. That's all it is. Any questions on that stuff you want to review? And then Max, you'll have to watch the chat because I can't see it while I'm up here. But normally on the screen, I get to see it. Okay? Thank you. No questions? Very good. Well, we're going to start with something that will become a lot more fun on Wednesday. I like to call it the power of the rectangle. So yes, rectangles are not the greatest for doing numerical calculations, but for developing formulas for ideas, it's much simpler to use rectangles than it is to use trapezoids or anything else. So we're going to look at the area between two functions. We're happy to have all takers. Okay, let's get ourselves a little graph. One function we'll call f of x. Have another function we'll call g of x, and we want to compute the area between f and g. So if I do f of x minus g of x. Okay, so when f is bigger than g of x, we'll have plus area. When g of x is actually larger than f of x, we'll have negative area, etc. Okay, so the way we think about the Riemann integral is, let's take a point, say here. We have f of x, and we have g of x. And draw an infinitesimally thin rectangle that has width dx. Okay, so if area equals height times width, what is the height of our rectangle that we've just sketched? And I'll put it back on the screen here. Okay, so the top of the rectangle is f of x, the bottom is g of x, the height is? F of x minus g of x. Wow, thank you. I already gave us that the width of the rectangle equals dx what? There you go. So then the differential area at the point x, I'm going to define to be f of x minus g of x times dx. So this is height and then differential width. If total area is the sum of the differential areas, then what do we get? All right, so we want area is going to be a sum of dA of x, and who knows, from A to B, and then, whoops, need my integral, need my sum sign, sum f of x minus g of x dx from A to B. Okay, so once you know how to define the Riemann integral for just a function, and when we were doing it for a function, effectively we had g of x equal to 0, and our rectangle height was always f of x minus 0, which is f of x. Extending it to finding the area with more interesting shapes is exactly the same calculation. And in the book, there's some nice pictures of different choices of f and g, and then actually plotting on the side f minus g and trying to look at, is those areas the same? Maybe that helps you, maybe it doesn't, but I think the better thing is to understand the power of the rectangle. So once you understand integration is summing up of differential areas, we get this. Okay, so let's just do an example, and it will bring up a few other properties of integrals. And what we're going to do with it next lecture, Wednesday, is be able to compute total mass of links of robots, things like centers of mass, points at where the link would balance on your finger, moments of inertia, which is how much resistance you have to rotational motion of links of a robot. All of that will just be a simple extension of this formula. And I know it looks very innocent, and it is innocent, but it has really interesting and fun consequences, is I guess what I could say. Okay, so let's get a nice graph going. I'm trying to make this nice. I got one half of it nice. Where's the copy and reflect? Oh well. This is f of x equals 2 minus x squared. And if I stretch this out a bit, there we go, that looks better. So this is a equals minus 2, and this is b equals plus 2. So that's f of x. And then g of x is going to be 0, and then equal to x. Whoops. That's x. I said x. I wrote 0. Okay, so in general, we've got g of x equals 0 for x less than or equal to 0, and it's equal to x for x greater than 0. So the area we want to compute is this area. And then okay, so we'll have positive area here where f is bigger than g, and negative area here where g is bigger than f. So we want to compute a equals the integral from minus 2 to 2 of f of x minus g of x dx. Now, since g of x is not a simple function like sine or something like that, and it essentially involves an if statement, this integral would be a lot easier to evaluate if we could first evaluate it over the region from minus 2 to 0, where g of x has a simple form, and then from 0 to 2, where g of x also has a simple form. So is this equal to the integral from minus 2 to 0 because if it is, we can fill this in pretty simply. It's minus 2 to 0. F of x is 2 minus x squared. Oops, this is x squared over 2, or that doesn't work, right? Let's see, x squared when it's 2 is 4 divided by 2, and we get 0. So that's x squared over 2. My apologies. Okay. And we have here 2 minus a half x squared, and g of x is 0, plus the integral from 0 to 2 of 2 minus a half x squared, and then just to show g of x there, dx. Okay. Can we break the integral up into two non-overlapping pieces? And then, even if we have that, we need to deal with the fact that our integral table contains monomials and not polynomials. We have monomials, not polynomials. Is the integral of a sum the sum of the integrals? Okay, the answers to these questions is yes and yes, as you know, because most of you have had Math 216. But let's just see why that's true from the very definition of what we're defining an integral to be. Everything online going okay still, Max? Okay, I can't see anything over here. Very good. Okay, so we've defined the integral as the area under a curve, and just simply by the definition of area, if we integrate from A to B, then we integrate from B to C, it really is the sum of the area from A to C. So the integral from A to C, we can take any midpoint, break up the integral, and end up with a very nice simple formula for the integral. So if A is less than B, less than C, the integral from A to B, I'm using F, let's call it h of x dx plus the integral from b to c, h of x dx, gets us the entire integral. Okay, and that just follows from our intuitive understanding of what area is. You can also do it with the definition of the Riemann integral, but you guys have seen enough proofs for now. The next result is proven in the end of chapter 3, and it's kind of obvious, but it requires interesting properties of limits. Suppose we have an interval with a less than b and functions f sub I takes ab to the reals 1 less than I less than n. Then for all constants alpha sub I in the reals, the integral of the sum is the sum of the integrals. The integral from a to b, alpha 1, f1 of x dx plus dot 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 alpha n fn of x. Let me remove the dx, sorry. Dx equals alpha 1 times the integral from a to b f1 of x dx plus dot, dot, dot. Okay, so if we have a polynomial and we know how to integrate monomials, we can break up the polynomial and simply integrate the individual terms. Okay? So we mark polynomial it's just a weighted sum. Okay, so results like this is how mathematicians build up integration for a large family of functions from a very small and limited family of functions like monomials. And this result that we've just stated is true simply because the limit of a sum is the sum of the limits. Okay, let you catch up there, and we'll go back to our original problem. Break it all down. And calculate the area. Okay, so we're tasked with evaluating two integrals. We're using two properties. The fact that if you stop halfway and enter and get the area, and then you continue on the other half of the area, you add them up, you get the entire area. So that allows us to break this up into pieces where it's easy to write down what f and g are, since g has an if statement in it, okay? It's a branch. And then we can break up the integral into applying it to each of these terms independently. We're good? I can tell by your excited looks that we're good. Okay. So, when you guys are talking to the younger students who have not completed Math 116 and Math 115, remind them that we cover it all. It's unfortunate for you guys, in part, but in the other part, I think we're going to be emphasizing some of the fundamentals that I don't know that you may have gotten in your first time through calculus. So that's what's going on here. So this is our first integral table. We have the integral from a to b of 1 dx. So using our results on monomials, that's a 0, where you raise it to power 0 plus 1, divide by 0 plus 1, we get 1. And this means b minus a. So this symbol, h of x from A to B is a very handy formula for h of B minus h of A. Integral from A to B, specializing our general formula to x squared over 2 from A to B, and then we get b squared over 2 minus a squared over 2 and then with x squared, raise the power 1, divide by the same power, apply the limits, b cubed over 3 minus a cubed over 3. Okay. So now let's apply it to A1, and that was the integral from minus 2 to 0 of 2 minus a half x squared dx. So this becomes 2, integral minus 2 to 0, the monomial 1 dx minus a half integral minus 2 to 0, the monomial x squared dx. So that becomes 2x evaluated minus 2 to 0 minus a half integral minus 2 to 0 x cubed over 3. What am I doing? I did the integral. Grizzle, turn your brain on. Minus a half. There's from our integral table, evaluated from minus 2 to 0. And so now we just do the algebra. We plug in 0 minus a minus 2 minus a half. Plug in 0, we plug in a minus 2. Then minus minus is plus, times 2 is 4. Minus 2 cubed is minus 8. Minus that is plus 8. Multiplied by minus a half is minus 4. That we then divide by 3. And so we end up with 8 thirds. 12 thirds minus 4 thirds is 8 thirds. Okay, so the two principles we're emphasizing is that you can break up integrals into smaller pieces, and then the integral of a complicated function can potentially be written as the sum of simpler integrals. And applying that to the first half of our area, we break everything down to where, knowing how to integrate monomials, we can then get the area under the first half of our function. Okay, now, question, who wants to go through all the details of the second half of that integral? Yes, I want to see every number. B, not so much. Is that what we're getting? Okay, that's kind of what I thought. Okay, so. Yeah. Okay, so just leave some space, and you can come in here and copy that in if you want. But here's the second integral. This was still f of x minus g of x, integral 0 to 2. We break it up to 2, the monomial 1, the monomial x squared, bring the coefficient out, and the monomial x. We do the integrals. Integral of that is x, 0 to 2. The integral of this is x cubed over 3, and this is an x squared over 2, all plugging in 0 to 2. And then it just becomes algebra, so the calculus ends pretty much here. Then it becomes just algebra, and if your dear professor has not made too many mistakes, and the area A2 is actually 2/3, and then the total area and if you want to write that as 3 1/3, we can, but I could care less, I'll be honest with you. Okay, so the power of the rectangle is that you come up with a rather complicated situation, and we're going to do this over and over and over for the rest of the week. Draw in your rectangle with infinitesimal width. Figure out its height, top and the bottom. The differential area is height times differential width. And then the total area is the sum of all of the differential areas. Now we're going to do the same thing with robot links, and we're going to be computing differential mass, and then adding up all the mass. We're going to be computing differential moments of inertia about the z-axis for rotation in the plane, and then adding up all of those inertias, and it's the same process. And I admit, this is not the most challenging integral that engineers will face. It's not the most challenging engineer that integrals will face, excuse me, okay? But it illustrates the basic property that when you're faced with a problem, if you can understand how to calculate the quantity for something so simple as a rectangle, then you can extend it to a much more complicated situation by using the power of calculus, which is a sum. Okay. Go away. Hide the controls, hide video panel. There we go. Okay, so we have one way for estimating area, and that's the trapezoidal rule. And the trapezoidal rule says you take the average of the two endpoints and multiply times delta x. Now, when we applied that to a sinusoid, we had to use something like 5,000 rectangles in order to compute anything remotely accurate, 10 to the minus 2 error, compared to quad GK, a professional package for doing that. You can imagine that if instead of, if this is xi and xi plus 1, here, this is what the trapezoidal rule would give you. If you instead fit a more complicated function to the point, and here suggesting a quadratic function, that then you'd get a lot better estimate of the area. So the general procedure really would be, given data points about your function, and given something that you know how to integrate, so we know how to integrate polynomials, instead of adding up rectangles, or instead of adding up the area in a trapezoid, add up the area under your more complicated function. Okay? And so if you do it with a quadratic, that's called Simpson's rule. And the area under that quadratic, here it is. We're going to go through how you come up with that formula. But it looks very similar to the trapezoidal rule. So the trapezoidal rule takes a weighted average of f of xi plus 1, with equal weights on the two endpoints, and then multiplies by delta x. Look what Simpson's rule does. This point xc is in the middle, so I'm suggesting you just take very, 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 very minimal notes here. We have 3 coefficients, so we need 3 points to determine a function that fits through those points. And when you do that and calculate the area, just like we just finished doing, you end up with a weighted average that is 1/6 on the left, 1/6 on the right, and 2/3 on the middle. That's the integration scheme. Okay, so what it corresponds to is precisely the exact area under this quadratic. And so that's how all numerical integration schemes are created. You propose the order of the function you want to interpolate through your data. And so here's a first order scheme. Interpolate a line through f of xi plus 1. And here's a nice convenient formula for a line. I have it centered about the left point. Okay, so y equals mx plus b, and instead of putting x, I have it shifted to start with the left end of our interval. We have 2 coefficients, so we only need 2 data points to determine the values of m and b. Okay, so all of these are posted. will be posted. This function y of x is said to interpolate our function f if they agree on the two endpoints here, xi and xi plus 1. Okay, so they interpolate if y of xi equals f of xi and y of xi plus 1 equals f of xi plus 1. Okay, so I'm defining the word interpolate. Interpolate means the two functions agree on a set of nodes that we have in the x-plane that we're using for our integration. And a first-order interpolation would be to use a first-order polynomial. And if you want to write it as mx plus b without the xi, more power to you, okay? But this is just a more convenient way to write it. And why is it more convenient? Let's look at how the coefficients fall out. If I set f of xi equals to y of xi, when I plug in xi for x, I get xi minus xi here, so this is 0, and so f of xi equals b, and I get the coefficient b in my first order interpolation. And then when I match the other endpoint, see, I'm trying to find the values of m and b to interpolate. Xi plus 1 minus xi is delta x, and you get a simple formula for the slope. F of xi plus 1 minus f rise over run, okay, for the slope. Okay, and so when you do a first order integration scheme, what you're doing is approximating the true area under the function by the exact area of the first order interpolate. Okay, so if you're doing a 0th order, then you just have a rectangle. So rectangles would be 0th order. The trapezoidal rule is a first order, and you can just check, if you do the area, you integrate this function with m and b that we just computed, you get this. And so we're going to take a break. When we come back, what I want you to do is just do this integral and show that you get the trapezoidal rule. You can work on it together. Okay, so on your own, actually, in fact, you can do that at home. When you come back, we're going to actually move to the second order method. And make sure you understand that. Because once you understand this, you can do third, fourth, fifth, sixth. You can do any order of interpolation you want. And you don't have to use monomials. Monomials are nice because we know how to calculate the area under them. But in Rob 101, you saw that it was much more efficient to fit functions with radial basis functions, for example. If they're still doing the precipitation mapping project in there. Okay, so let's take a break. And then we come back, I'm going to set you up for knowing how to derive on your own or understand what's under the hood for all of these different numerical methods, which are how I as an engineer and you as engineers will be computing integrals. You won't be doing the analytical forms that you were taught in Math 116. You're going to be mainly using numerical methods, and you should So you should have a fundamental understanding of how those things work, and that's what I'm after here, okay? So let's take a break. Everything still going?
Yeah.
Okay, I'm going to answer the question that was on Zoom. And you guys can continue at a little bit lower level. I'm going to answer the question that was on Zoom. So the question was, why compute the area under the quadratic approximation of the function instead of just computing the area under the function? Is that it? Yeah. And the thing is, suppose f of x was e to the sine of x cubed plus square root of 1 plus x squared, for example. Using the classic techniques that you may have already seen, some of you, in Math 116, things called integration by parts, things called integration by substitution, etc. Those techniques will fail on that function. There is no antiderivative. And so you're forced into doing numerical calculations. Now, hence, the idea is, and so pretend that this blue curve is that really complicated function and you really want the area under it because it's going to help you get the moment of inertia or the volume of revolution of some particularly exquisite device that is going to make you a lot of money in your startup. But you need some precision in the calculation of its mass or whatever. Then you want to get a very good numerical approximation. If you use rectangles, it's going to take a lot of rectangles to fit that function. Here, the way I've drawn it, the trapezoidal rule and the rectangles will give the same thing. But if I were to approximate the function with a quadratic, and since I can compute exactly the area under a quadratic because it's a polynomial, then I can sum up those areas much more efficiently than summing up the rectangles as we would with Riemann sums left and right. Does that help? Okay. Is there a follow-up?
Yeah, they just want to know if they could integrate the quadratic itself instead of doing Simpson's rule, but some are...
I see. So Simpson's rule is this. You can. So once you fit the quadratic, this is Simpson's rule. It is the result of integrating the quadratic, and that's what we're going to go through right now to see the relationship between those two. So they're exactly the same, and the point is, instead of you having to go through from I equals 1 to n is 10,000 and doing 10,000 integrals of quadratics, if you have this simple closed form solution, that is a very easy calculation in a for loop to do. Okay, so getting the closed form solution is how these fast numerical integrators work. And you get more accurate numerical integrators by using higher order fits to your curve. Okay, so here we're just once again explaining if you were trying to come up with a general procedure, and this one gives you the trapezoidal rule, which we all know and love, okay, now because we can calculate the area of a rectangle and a triangle and add them up. But if we think about it more abstractly, you fit a line using your two data points. To interpolate, you need to find m and b such that the line and the function agree. So here, I drew the picture, but when you're doing it in Julia, all you have is the values of the function and the values of x. And so you need to compute m and b. And then that's what the interpolation process is. You impose matching at the nodes that you're given here, xi and xi plus 1. And so because it's aligned, we've been able to solve for those coefficients since we were, I don't know, 14 years old, something? Yes, please.
When numerically solving, is there a way to find out, or like, I guess prove like how the error bound drops, how it gets more accurate when you use like a higher degree one versus like just adding more rectangles?
Yeah, so the question was, if you do this, and you're just using rectangles or trapezoids or whatever, you have a couple of choices. You can do higher and higher order approximations on the given xi plus 1, or you can simply take 10 times more rectangles instead of using a fifth order polynomial and that. So that's what a course in numerical analysis covers. So they go through and they look at the stability of your calculations, and they show how to actually propagate error estimates for it, okay? So that's what some of the alternative courses you would be taking if you were taking this for your entire math 115, 116, and 216, so you freed up some of your math to take fun things like a numerical analysis course. You could learn how to do that. And then that would help you make a more informed decision instead of just going, I'm using quad GK, okay, which is a good one, But when you're designing an algorithm and you're launching it into space, you may not have it may not have the computing space and power to run something like quad GK, and you want a simpler algorithm where you've chosen these bases functions like monomials or something else that better fits the data you have. Okay, so the general procedure is you propose an order of the interpolation, you solve the interpolation conditions, and then you compute the exact area for this first order approximation. And then that would be, in this case, clearly better than the rectangle would have given you. So this is, and you can go through and figure out that this gives you the trapezoidal rule. It should, right? It has to. So you've got to integrate a linear function. So you've got a constant, where's my function? You've got first order in x, so then you've got two constants here. Okay? So second order method, this would give Simpson's rule, okay? But if you understand what we're doing here, you can change it to third, fourth, fifth, sixth, seventh, eighth, whatever you need to get the precision you want, okay? You understand how those things are done. And then there's nothing magic about putting polynomials except we know how to integrate polynomials. If the function is periodic, you might fit it with a sum of sines of frequencies. And if you've heard about Fourier series, it's once you know how to integrate sinusoids, which many of you do from Math 116, you could get the area under the sinusoids very efficiently and then calculate the area under arbitrary periodic functions, okay? So these methods extend. That's what I'm trying to say. So let's just understand, want to interpolate a quadratic through our points. I'm proposing the quadratic to have a second order term, a linear, and a constant. So that's three unknowns. We need 3 data points, and I'm proposing that we add a midpoint here, xc. So xc is the midpoint between those. And if xi plus 1 is xi plus delta x, so we do a uniform grid, we take the midpoint, then this is xi plus delta x over 2. So what I'd like you to do just at your desk now, So your little bit of active work is to solve for A, B, and alpha, beta, gamma such that this quadratic interpolates a function f of x. So how do you find alpha, beta, and gamma such that our quadratic here matches f of x and at xi, xc, and xi plus 1. So solve for these, write down the equations that these three things need to solve. You don't have to solve the equations just yet, but set up three equations and three unknowns such that for a function f of x, this polynomial interpolates it. Okay, so just work it out on a sheet of paper. We'll go through the answer, but just want to see if you can, well, you want to see if you can do it, because in homework 3, you get to do the cubic version of this. It's called Simpson's 3/8 rule. Okay? So it's the next level of version of Simpson. Justin, you don't have any paper with you? Is that your problem? You can work with Devin if he would be so kind as to let you look at what he's writing on his tablet. Okay, so everybody see what they should be doing? Just as we could easily solve for B and M by taking the linear equation and matching the function values, now take a quadratic for the interpolating function and solve for alpha, beta, and gamma such that you do xi, xc, xi plus 1. Okay. So see if you can find the formulas that alpha, beta, and gamma have to satisfy. What you find out is you only have to do that once in your lifetime in the history of humanity, because you can reuse the formulas at all other values of xi, f, etc. Is there a good way, Max, for the people online to share with you what they're getting? Or?
Yeah, I think probably.
I think they can type in a formula. Or just describe it and you can go, yeah, you're on the right track. So Max and I can walk around and see if you need some help. Or no, you'll work with the people online and I'll check the people in the room, Max, and give you 5 or 10 minutes. That's, excuse me, maximum, not Max, not Maxwell. Formulas you need to be writing down. Gamma is, how does it relate? I don't see the function values here. So you want to match this with the function values. So you're going to have f of xi equals q of xi. And you plug in xi, you get gamma equals, this is f of q. because you see, this is the function, and these are the values that you have. For example, coming off of drum, you have those values, right? And then, so that, and this is an artifact because we know how to integrate in polynomial. Related to the f's, like up there. Xi is related to f of xi, xc is the point. Yeah, once you get going, it's going to make homework 3 trivial when we do this. Making any progress?
I'm sure if I'm doing something right, just simplify it and substitute some
Yes, you've got formulas up here. The xi is just given, and the center point is xi plus delta x over 2. So take the quadratic, the bottom there above the word interpolates. When you plug in xi, what do you get for q of x? Yeah, don't expand this out. Definitely not. Okay? Don't expand it out. You drive yourself crazy. Okay? Making any progress? No, that's some other class. That's math year 15. Okay. What do you get for gamma? Find the xi. Cool. Then when you plugged in xc into q, what did you get? So I think many of you see when you plug in xi here, this vanishes, and when you have f of xi equals q of xi, you have f of xi equals q of xi equals gamma. So gamma is trivial. Okay, next formula, f of xc equals q of xc. Now plug in xc, which is xi plus delta x over 2. So what does this become? What does this become? Okay, and then do the same thing. F of xi plus 1, which is f of xi plus delta x, and then replace x and get a relationship for alpha, beta, and gamma. Does that make sense?
Yep. I'm just wondering why this is wrong. In this substitute, xi, xc, and xi plus 1, because we know once we have that, we get 3 equations.
Yeah, 3 unknowns. Yeah.
3 equations and 3 variables.
No, you have alpha, beta, and gamma. We have 3 equations and 3 unknowns.
Oh, xi, xc, and xi plus 1 are
No, those are known. Those are given.
and alpha with the compound would be the only unknowns.
Alpha, beta, gamma are the only unknowns.
But every time we substitute a value, we get a different equation. So we get 3 variables and 3 equations, and we get this on.
Yeah, it'll be linear in alpha, beta, and gamma. Using all of one right down the solution.
So this works out to a just substitute.
That's what interpolation is.
Okay.
It's just setting up the equations. You got it done?
Wait, so so
It's getting close. When you plugged in f of xi, so what is that? Alpha times, what do you got there squared? Delta x? Yeah, that's correct. Yeah, yeah, that's 3 equations, 3 unknowns. Write it as in the form ax equals b. Get an A matrix, and get it times alpha, beta, gamma, and then get the right hand side. Okay? See what you're doing? Yeah. Is it farther along? Yeah, f of xi, so that's alpha delta x, and the other one delta x over 2, and then gamma. So now, notice everything is linear in alpha, beta, and gamma. These 3 equations. I mean, this one's trivial, okay, but that's fine. It's still an equation. So write it as ax equals b, where x is alpha, beta, gamma, and b is f values that you have measured. And then the A matrix is just going to consist of both things that are multiplying. Yeah. If you can get that going. You got it done?
well, this is what I have. So basically, we plug in x minus xi, it basically goes to 0, and then you get g and
Yeah.
g, and then you can plug that in to get this, and then you can just solve it there.
Yeah. So you've reduced it to two equations and two unknowns because you eliminated G or gamma right away, which is how we did it too. Okay. And what I'm going to do here is keep the three equations and three unknowns, because when you do it in your homework, yesterday, like this week, it's going to be messier if you eliminate it and all that stuff. It would be
Better do it all at once.
Yeah, you could write it as four equations and four unknowns, and then you would just use the symbolic solver in Julia to get the answer in terms of the measured values, which is the f of xi's, etc., and then the delta x, which is your step size for the integer. Pretty cool. Yeah.
So this is not.
It's not working. Something's working over here. Yeah, so don't do any integrals yet, just the equations. I think you're getting there. You see these things? They don't even work very well, so you have to use more volume. Yeah, so let's point here. This is the interpolation condition. So f of xi equals q of xi, which means I plug in xi here, 0. I plug in xi here, 0, and I get f of xi equals gamma. And then I've got interpolation conditions at xc. But xc is xi plus delta x over 2. So this becomes delta x over 2, and this is f of xc. And you get linear relations between alpha, ABG or alpha, beta, gamma. Now you have to do this exact same thing at homework, and you may need it for, who knows, some drone projects, some team project where you need better integration, and you can't run something like Julia or MATLAB or C++ to just use the given integration package, and you need to build it yourself. And everybody else on the team from the normal math class just goes, I don't know how to do it, and you go, oh wow, I know how to integrate whatever Bessel functions of the 19th kind, and I can interpolate those, and I've got it, okay? So. Okay, so I think you guys got progress on that. So here's the solution, and of course you'll have them when I post them, which is really soon. So we want the interpolated function to agree with the data points, and the red curve is just imaginary because we may not even have that. So if you are getting the data off of an IMU, all you have are the xi's, okay? So you've got your data points, and you want to fit a function here, because so far in this class, we've only learned how to integrate monomials, which means we can do polynomials. We're doing a simple interpolating function, but in Quad GK and other Julia packages, they use more interesting functions that interpolate really well. It doesn't take as many coefficients as a monomial would, and yet people have figured out closed form solutions for the area of the interpolating function. So here, these are the interpolation conditions. So we just write them down. F of xi equals q of xi, and plug in xi for x. And so gamma is trivial. F of xc is xi q at xi of delta x over 2. We get delta x over 2 squared and delta x. And then f of xi plus 1. And that's xi plus delta x, so when we subtract off xi, just the delta x remains. And so I'm just pointing out that it's 3 equations and 3 unknowns. You know these, so that's given to you. You choose your step size in your integrator. You can go on Julia using some of the symbolic stuff and just calculate the determinant. It's like 1/3 delta x cubed or something like that. So as long as delta x is non-zero, the matrix is invertible. Here, I just went through and solved it as, process of elimination. Then I checked it with ChatGPT 01. I checked my calculations there. I didn't fire up Julia. I should have. And so instead of doing first order trapezoidal rule, our AI in this second order one is the exact area from xi to xi plus 1 of this function with these values for alpha, beta, gamma. So it's area under the interpolated quadratic. Okay, so here's one more thing where I want you to pay attention. These integrals, so if I were doing a third order, I'd have x minus xi cubed. And if I were doing a fourth order, I'd have x minus xi to the, okay? They're super easy to do. I claim that x minus xi from xi to xi plus delta x is the same as from 0 to delta x of z squared. And we know how to, so you don't have to multiply this out, is what I'm trying to avoid, okay? Because as soon as you do more algebra here, you're going to make a mistake. But if you can replace this with z and get simple limits, and then you get z cubed over 3, it's much nicer. Why does that work? Here's our quadratic, say fit through xi to xi plus 1, okay? There's our quadratic. And we want to do this integral. Let me draw another line right underneath it, okay? Z, and let xi be the origin here. That means that z is x minus xi. This thing that's under the integral, the integrand. Okay, so this is the same picture. xi plus delta x is 0. Whoops, come on. 0 to delta x then, because z is x minus xi. And this area in x and this area in z, there's no difference. So this integral is the same as this integral. And it's the same for the linear term and the constant term. And so this becomes z cubed over 3 from 0 to delta x, and so we just get delta x cubed over 3. So that's a lot easier than messing with this integral, okay? So you just do a shift, change of variables. And then, to get your Simpson's rule, you plug in for your coefficients, and you guys, we got the simultaneous equations for it. If you're on Julia using the symbolic stuff, you just solve for these. You plug in all of these terms, and then you let the computer do the algebra for you. And this is the second order integration scheme. It's 1/6 times f of xi times delta x, so 1/6 times the endpoints, and then 2/3 times the midpoint. And that gives you a better approximation than the trapezoidal rule, which is a half times the two endpoints, all times delta x. Pretty cool? You see how you could extend that to a cubic, to a quartic? And as long as you're doing computer algebra, it's okay, because you'll mess it up, or I'll mess it up. And that's how you derive these higher order integration schemes. Any questions online? Yeah, so I'm not doing the algebra. It's done in the textbook if you want to go through it. You can do it at home and double check that this is what you get. Or fire up U of M GPT, call these A, B, and G like Elvis was doing. Give it, call this FI, call this FC, call this FIP1, FI, just give it simple names for the variables. Plug them in, multiply by these integrals, and say, hey, simplify this for me. And this is what will pop out. Okay. And then as a human, you can do it, and it only pops out one time out of 4. Okay. as a machine. So actually, so Simpson's rule you guys can do if you just take your time. And that's all I want to do for today. So if you have just questions, I'll be happy to hang around and just answer questions. And then Wednesday, we're going to use our integration methods to calculate properties of robot links. Mass, center of mass, moment of inertia, things like that. And then move on to a new chapter.